Okay, today we're going to be talking about loci. So loci is the plural of locus. And a locus, in mathematical terms, is what we define as a path traced out by a point as it moves following a particular rule. Now the rule can either be an equation or an inequality. So we're going to be looking at the locus of points in R-grand diagrams. So in an R-grand diagram, we first need to interpret the equation or inequality we've been given. So let's begin by looking at circles. So we're going to look at circles. And to keep it simple, we're going to start with a circle on the centre of the origin, so 0, 0. Now let's consider we have the modulus of some complex number z equal to r. Or we could have the modulus of a complex number less than r. Or we could have the modulus of some complex number less than or equal to r, where r is constant. So in this case, we're looking at a length position vector representing this complex number z with this by this constant number. However, the argument, so in these examples, r is the position vector of the complex number r, but the argument can vary. So if you think about, here's our R-grand diagram, real z, imaginary z, then we have this vector r, and it can go anywhere in this circle. That is a terrible circle. Let's try and draw that a bit better. So if z equals r, we're going to have this line here is our locus. Right round here, that is our locus. It can just go round this route. But if z is less than r, then it can't be r, so it's the area inside. So it's this inside the circle. But for the modulus of z less than or equal to r, it can take both. It can take both the circular route round here, but it can also take the values in the middle. need to change my colour back. There we go. So what this tells us that for z equal x plus iy, the modulus of z equal to r is the circumference of the circle centred at the origin. For the modulus of z less than r, it's all points within the circle but not the circumference and for z less than or equal to r, it's all points in the circle and the circumference. So let's do some examples on separate R-gram diagrams. Sketch the following. Sketch these loci. So firstly, we want to do modulus of z equal to 5. So here's our R-gram diagram. And this is how we put some values on it. And we'll have 1, 2, 3, 4, 5, up to 6, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. So we've got, for this, we've got the circumference of a circle centred on 0, 0 with radius 5. So obviously you do it on square paper and it'll be much more accurate. So this is only the circle, not the points within the circle. And you should draw it as just a solid line. Now, what about modulus of z less than 3? So we've got a circle centred on 0, 0, radius 3. This is going to look like a dodgy circle as well. Oh no, so I don't want to do that now. Because it's not the actual circumference, what we're going to do is we're going to draw it as, we'll draw our circle as a dotted line. So by drawing it as a dotted line, we're indicating that it's the circle, but it's inside the circle. All the points, and we can shade in the circle, that is all points within the circle, but not the circumference. And let's do another one. This time, no surprises, we're doing the modulus less than or equal to 4 this time. So again, it's a circle, centered at 0, 0, and the radius this time is going to be 4. So we'll do our argand diagram. So we've got 1, 2, 3, 4, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, minus 1, minus 2, minus 3, minus 4. So this time we do a solid line because it includes the circumference, and we also shade in the center because it's also all points within the center. Okay, obviously not all circles are centered on the origin. So what about circles? I'll put back onto black. Circles centered at point A, B. So we're going to consider the modulus of z minus z1 equals to r, and we're going to consider the modulus of z minus z1 less than r, and we're going to consider z minus z1 less than or equal to r, where r is a constant and z1 is a fixed point a plus bi. So we need to understand the vector representation of this number. So let's consider z minus z1. So we're going to let P, some point P, be xy, and it's going to be a moving point represented by z equals x plus iy. And we'll do that on our Venn diagram. And we're going to let Q be point AB, and it's a fixed point represented by Z1 equals A plus BI. So let's draw this on our Venn diagram. So we've got P up here. P is xy. And here is P's position vector. And we've got Q here. And Q's fixed. And it's A, B. And we will draw a line between them here. So Z is going to be OP, and Z1 is going to be OQ. Therefore, PQ will be, so PQ here is minus Z1 plus Z, which is Z minus Z1, which is what we've got here. So now, if the modulus of Z minus Z1 equals r. Therefore, the length of PQ is equal to r. So this length here is r. Now, for this setup, what this means is when z minus z1 equals r, it's the circumference of a circle centered on point Q. So if you think about it, we've said this is fixed and this is movable. So what we then get is this can move around like this. And it'll be a circle. So when it's z minus z1 equal to r, that is going to be, just like previously, the actual circumference. And then z minus z, that's not drawn nicely, z minus z1 less than r is going to be all points within the circle centered on AB, but not the circumference. And z minus z1 less than or equal to r is all points in the circle and the circumference. Now, we will do some examples to see how this works. It will hopefully become clearer. So on separate R-gram diagrams, sketch the Loci. So remember, the Loci is the path that a point maps out with predetermined rules. So that's what we're actually, always keep that in mind, that's what we're doing with these. So we've got z minus 2 plus 4i equals 3. So here, remember z minus z1, so z1 is going to be equal to 2 plus 4i. So this gives us, so this is going to be a circle centered on, so this is our x coordinate and this is our y coordinate, so 2, 4, with radius 3. So 1, 2, 3, 4. I'm not going to do all the coordinates. Oh, it's not minus at all, is it? 1, 2, 3, 4. So it's 2, 4. So it's up here. Radius 3. Something like that. That's meant to be r equals 3. It looks dodgy. And that's what that would be, because equal to. So it's this solid line. Draw them a bit more carefully when you're drawing them yourself. What about z minus 3i less than 4? So z1 is going to be equal to 3i. Now think about this. We said this is z minus z1 is going to be less than r. So here we've got z minus, then we're going to open a bracket up and put what's our 3i less than r. So the minus is from here. So Z1 is actually 3I. So that's something to be really aware of when we're thinking about these circles. It's Z minus Z1, so you've got to make sure you've got your minus here and you don't put minuses where they're not meant to be when you're looking to find out what Z1 is actually going to be. So we've got a circle with centre, there's no X, there's no real component, it's just 0, 3, radius 4,
Are you done your video, Mum?
1, 2, 3, 1, 2, 3. So it's centred up here, radius 4, and there we go. Oh, wait a minute. Radius 3, it's less than, so we do our dotted line this time. So it's going to look like something like that, and it's going to be the points within the circle, but not the circumference itself. Okay, let's do another one. So this time we have Z plus 5 less than or equal to 5. So again, let's think about what Z1 would be. So Z minus, and we've got 5 less than or equal to 5. So our Z1 this is a positive, so this must be minus to get put minus and minus to make a positive. So Z1 must be minus 5. And now we've got a circle. There's a minus 5, there's no imaginary component, and the radius is equal to 5. So here's our minus 5. There it is there. This time it's a solid line, and it's the points inside as well, because it's less than and equal to. Okay. Let's get rid of that. Let's get rid of these. Okay. Now we're going to think of half lines and part lines. So this is when we're going to be having to consider what is the argument of z minus z1. And we're going to call it alpha, where alpha is a fixed angle and z1 is our fixed point a plus b I. So with our previous definition, z minus z1 can be defined with z is, let's draw our points on an R-gram diagram first. So we've got point here, P, X, Y, and we've got our point Q again, A, B. And here's our vector X minus X1. Now, draw this here. So Z is OP, Z1 is OQ, and PQ is equal to Z minus Z1. Now we're going to define the argument as the angle between the direction of the a direction parallel to the real axis and vector PQ. So this here is alpha. This is how we define alpha. Points below Q are not part of the locus as the angle made between these points and the relevant horizontal line is pi minus alpha and not alpha. But what happens if we have a situation with the argument, and this time it's z1 minus z? So this would look like, so we've got our p here, and here's our q. So this time we've got our x1 minus x is going to be in this direction, and this time the argument is going to be defined with this angle here, which we're going to call beta. So z1 minus z is equal to minus z minus z1. And again, similarly, the points above P are not going to be defined as this locus, because these points and the relevant horizontal line are going to be pi minus alpha, beta, and not beta. So same argument as the one above. Okay, I think it's simplest to do some examples to see how this looks in practice. So on an R-gram diagram, sketch the Loci z, the modulus of z equals 4, and the argument of z plus 2 plus 3i equals pi over 4. I want to show that there is only one complex number z that satisfies both Loci. And then label this point as P. Okay, so let's begin with the easy bit. So we've got modulus of z equals 4. So let's draw this to begin with. Oh, that's a very bad axis. There we go. And we know that's just going to be a circle, radius 4. So there's our 4. So 1, 2, 2, 3, 4. 1, 2, 3, 4. Minus 1, minus 2, minus 3, minus 4. Minus 1, minus 2, minus 3, and minus 4. There we go. Now, let's consider this. The argument of z plus 2 plus 3i equals pi over 4. So our z minus z1 equals z plus 2 plus 3i. So z, now we've got our minus, let's put this into brackets. This is a positive here, 2 is plus 2, but we have to have a minus here, so that must be minus 2 because they'll cancel to give us a positive. Similarly, this is plus 3i, this must be minus 3i because we minus here, but the minus 3 would become the positive. So our z1 is equal to minus 2 minus 3i. So we've got a half line from minus 2 minus 3 at an angle of pi over 4 radians. So minus 2 minus 3 is going to be here. So we've got our dotted line, and then we'll have our line up here. So this will be P, and this here, I'll write it up here as pi over 4. That's our angle here. So this must be our P. Okay. Perpendicular bisectors. So if we had z minus z1, the argument equals z minus z2. That's our first scenario. Our second one is going to be z minus z1 less than z minus z2. And thirdly, no surprises, z minus z1 less than or equal to z minus z2. What does that mean? So first let's define z1 as a plus bi, and z2 is c plus di. And point P, X, Y is a moving point represented by Z equals X plus IY. And QAB is a fixed point, and that Z1 equals A plus BI, and we'll have point R, CD is a fixed point represented by Z2 equals C plus DI. So in our first situation, Z minus Z1 equal to Z minus Z2. Point P moves so that it is always the same distance from Q as R. Therefore, the locus is a perpendicular bisector. So you think you've got, actually I'm not going to do that there, I'll do it up here. So you've had P and you have, no, you've got Q and you have R, then you'll have this vector between them, and then you've got this line here. Perpendicular bisector would be the locus. This would be, the point would go up and down here. So it's always equidistant between, it's always the same distance between Q as it is from R. if we had z minus z1 is less than z minus z2, then all points such that P is nearer Q than to R. Therefore, the perpendicular bisector marks a boundary. And finally, z minus z1 less than or equal to z minus z2. So all points such that P is nearer Q than R or equidistant from Q and R. So the perpendicular bisector marks the boundary of this region. Okay, so let's look at our diagram. So here's our perpendicular bisector. So in this situation, the point P is nearer to Q than to R, so it's anything down here on this side of the perpendicular bisector, but when it's less than or equal to, you've got all the points on this side of the perpendicular bisector, including the bisector, but not on the other side, would be your locus. So let's look at an example on an R-grand diagram. Sketch the locus z minus 4 plus I equals z plus 5I. So let's think. What is z1? So let's write this first. Z minus 4 plus I. So it's going to be z minus 4 minus 4. This is a plus, so we need to have a minus here. So z1 is going to be 4 minus I. And our other one was z plus 5I. So that's going to be z minus 5I. So z2 must be minus 5I. So for the perpendicular bisector, which we need to find the midpoint. We need to find the midpoint between P and Q. So Q is going to be 4 minus 1, and Q is going to be 0 minus 5. And so with the midpoint, we're just going to use our midpoint equation. So we'll have 4 plus 0 over 2, and minus 1 plus minus 5 over 2, and that gives us 2 minus 3. So let's mark these on our diagram. So we have 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and minus 5. So our point Q is 4 minus 1. So this is point Q, and P is 0, minus 5, so this is point P. So this is the line between them, and our midpoint is 2, minus 3, so about here. Okay, and we want to find the Cartesian equation of this locus. So we need to think, what is the gradient of PQ? Well, that's just going to be y2 minus y1 equals x2 minus x1. So for it's going to be minus 5 minus 1 over 0 minus minus 4, not minus at 1, there we go. So that's going to be minus 4 over minus 4, which is 1. Therefore, the gradient of the perpendicular bisector is going to be minus 1, just because of, remember, m1, m2 equals minus 1 when they're two perpendicular lines. So that's minus 1. Now we can just use our equation of a line, y minus y1 equals mx minus x1, to find the equation for the locus. So and we'll use the midpoint here, so y minus 3 is going to be y plus 3 equals minus x minus 2. Working all that out, we'll get y equals minus x minus 1. And that is the equation of our perpendicular bisector here, which is the locus of that satisfies this set of rules. So I hope that helps.